Hello everybody. Thank you for joining us on Saturday afternoon. Uh, I know it's a little sleepy afternoon in this summer weather, but thank you for joining us. So today we have Dr. Subhra Majhi, who's joining us from Curtin University, Australia, and he's going to be talking about monitoring bridges with waves. And he was a civil engineering student here at IIT Gandhinagar in 2012 to 2014. And he finished his PhD in 2020 from Curtin University, Western Australia. His research interest is innovative, non-destructive, non-invasive inspection techniques for built facilities. He has co-authored 14 journal articles in SCI index journals and co-authored 6 Australian and international peer-reviewed conference articles. As per his Google Scholar, his co-authored research articles have received more than 300 citations. During his PhD, he closely worked with the research team to operatize the laser ultrasonic monitoring lab at Curtin University. After that, he has used laser ultrasonics to monitor corrosion in reinforced concrete. He has also developed an imaging paradigm to image corroding concrete reinforcement. As part of his first post-PhD placement, he has coordinated a large industrial research project as a researcher. This project was funded by the Main Roads Western Australia. He currently is an associate professor at Curtin University, and along with his research, he teaches undergraduate and postgraduate civil and mechanical engineering students. And as part of his community outreach activity, he volunteers with Red Cross Australia, where he recycles apparels and promotes sustainability. So this is Subhra Majhi, and thank you everybody for joining us. I'll pass on the mic to Subhra.
Thank you, Manasvi, for this wonderful introduction. So, just a quick clarification: I'm an associate lecturer.
Oh,
so
I'm so sorry.
I'm still starting. So maybe one day I'll become associate professor.
Yeah.
But anyways, thank you, Manasvi, for your introduction. And now I will start my presentation today. And the topic of my presentation is monitoring bridges with waves. As we go along with in this presentation, I will explain how we are going to monitor bridges with waves. So first comes first the background. So when it comes to the life cycle cost analysis of any structure, there are three key components to it. One is time, quality, and cost. And when it comes to cost, there are two major aspects to cost. One is an operational cost, another one is a maintenance cost. And when it comes to cost calculation, mostly the operational cost is considered and the maintenance cost is not considered that much. So that's why we need to pay attention to the maintenance cost. Because if we don't pay attention to the maintenance cost, there can be severe challenges to monitoring these structures. Okay, so now let's have a look at this case study. So what can poor bridge maintenance and monitoring do? So this is a bridge. This bridge is called Ponte Morandi. It's in Genoa, Italy. And this bridge collapsed in 2018. And the big section of the bridge, as you can see here, is here on the ground. And I think around 39 or 40 people died because this bridge fell on the series of houses and roadway, which is here. And this bridge served about just over half of its service life. The reason why there was a premature failure was this region, Genoa, is very close to the ocean. And that's why there was corrosion in the steel reinforcement bar here. And the corrosion was not detected until very late, or in this case, the corrosion was not detected. And as a result, there was severe structural issues in this particular bridge leading to its collapse. So not only there was a huge cost in terms of loss of property, but also there was loss of human lives, which was very bad. Okay, so now I will give you some perspective into what things happens in Australia, the place where I'm based in now. So in Australia, there are about 53,000 bridges, small and big, and these bridges are maintained by various monitoring organizations, and most of the monitoring operations is done by visual inspection. So what do you mean by visual inspection? So there is an inspector, or there are a series of inspectors who goes to the bridge they have a look at different aspects of the bridge and try to give a report about what is the condition of the bridge. As you must have noticed that this is a very labor-intensive method and a very subjective method, because it all depends on what the inspector sees on that particular day. And my experience with working with qualified engineers, I have understood that the very experienced engineers, they are able to find out defects. But what about engineers who are upcoming? And also the experienced engineers can only find out defect only after some signs of problem appear in the bridge, not before that. So what are we going to do for a situation so that bridges like this, they don't fall down? Let's see, what are we going to do? So this is like a solution scheme. So what we do is we introduced sensors in bridges and bridge components, and the sensors, they collect the sensor data, send it to the cloud, and these clouds, they use different algorithms to have a classification, to have classification and to give suitable reports to the inspectors, who would again go there and do detailed inspections. And based on their inspections, we can take a decision about whether the bridge needs to be retrofitted, replaced, or it's in a good shape. So the decision about a bridge is made, and then we do the monitoring part again, and based on a loop of constant monitoring and reporting of the structure's condition, we are able to monitor how the bridge is performing. But again, for that, the sensors needs to be in place in bridges. Okay, so what type of sensors are we talking about here? As the topic of my presentation says, we would be monitoring sensors that make waves, that makes waves in those structures, and based on how these waves behave in these structures, or in our cases bridges, we are able to find out what is going to happen, what's the state of deterioration in those bridges. Okay, so as I have just now said that we'll be using waves, I will explain you now what these waves are, how we are going to use these waves. Okay, so these are the different ways by which we will be using these waves. One is passive system. In passive system, we are just listening to waves that are being generated in structure because of emanating cracks. So when there is a crack form, there is a shock wave that is generated, and the shock waves are being picked by the acoustic sensors. This is one type of monitoring. It's called passive monitoring. Here, we do not have information about past activity, but only situations where the damage is emanating that can be picked up. Next type of system is active system. In the active system, we send energy into a structure, and this energy is sent in the form of waves. And these waves, these are stress waves. These stress waves, they go inside into the structure. They interact with any defects or whatever is happening in the structure, and based on how much of the wave has traveled through and how much of the wave has reflected, we are able to give a prediction about what is the condition of the structure. And this can be done in two ways. One is through traditional piezo-based devices, where we have piezo sensors that are on the structure, and these piezo devices, they send a wave, and another piezo device, they receive the wave, and based on our interpretation, we try to find out what is going on. This can be done in another way by using lasers. So here what we do is we use a high power laser, which is here, and we ablate the structure. So basically what happens is the laser, it sends a energy pulse. It's like a jolt of energy. So this jolt of energy goes and hits the structure, and it causes a mechanical wave. So this wave goes into the structure, and the wave is detected by another measurement device, which is called as the laser vibrometer. And thus, by monitoring how the wave behaves, we are able to find out what is going on in the structure. These are the two different ways of monitoring structures. There is another way. We can image what is happening inside the structure. We can find out what are the hidden embedments in the structure, and monitor those embedments over time and find out what is happening in the structure. So these are the different ways by which we can use waves to monitor structure. Now we will go in detail about how these methods are used. So these are some experimental setups that are present in our labs at Curtin University. So this is the laser system. So this is a pulse laser. It shoots laser beams into the structure. In the structure, we are just monitoring a part of the structure, that is just the steel bar. So we hit the steel bar with a laser pulse generated by the pulse laser, and we measure using a laser vibrometer. Other than that, as we discussed, we can also use piezo-based devices. Piezo-based devices, they look like this. The advantages of piezo-based devices are their response is narrow-banded, but the disadvantage is they can generate only a certain extent of energy. When it comes to laser, we do not have much of a control over what is being generated through the laser, but the amount of energy that is generated by the laser is around 3 to 4 orders of magnitude higher than the piezo. So that's why laser is a promising solution for monitoring structures of long lengths, because civil engineering structures are few meters and at times maybe a few kilometers in length. So we need a large source of energy to excite such big structures. Now, let's come to our first task, because the first problem statement, we have seen that when there are large structures close to the ocean or marine environment, there is a chance for corrosion. So what we have done is we have used a study to monitor corrosion in steel bar. So what we have done is we have corroded a steel bar to various levels, and we are trying to monitor this steel bar through ultrasonics. So this is the first step. So this is a steel bar. It's a meter long bar, and we are exciting it with piezo-based ultrasonic devices, and we are seeing how the signal behaves with regards to different stages of corrosion. So this is a typical signal, how what can be seen in a steel bar system. And then we do different types of analysis. First is the time series analysis, where we are seeing a time signal, and based on the time signal, we are trying to find out when the first wave arrives, when the second wave arrives, and what is happening in between. Other than the time signal, we also use a Fourier analysis. We convert the time signal into the frequency domain and try to understand what is happening in the signal. So my background is civil engineering, and a lot of the signal processing I had to learn on the go by getting in touch with the resources available online and talking to people. Okay, so this is something fun that I learned on the way. So my task was to understand how Fourier transform actually works. So in the last slide, we have seen all this math, and we know what the math can do. But I had this curiosity of knowing like what exactly is the physical implication of this. So I got this example, and I use it quite often in my teaching, and I think you like this discussion. So a time signal is nothing but a packet of M&Ms. So people who live in the West, they must be very aware with what an M&M is. In India, there is this chocolate called, I think it's called Cadbury Gems. So M&M is like the bigger version of Cadbury Gems. So yeah, so I'll give you the analogy now. So let's say the time signal is like a packet of M&Ms. And the M&M packet, what do we have? We have different colors and shapes of M&Ms. Now, what is happening in the time signal? So in the time signal, it's like on a conveyor belt, different colors and sizes of M&Ms are traveling at different times, and their time history is recorded here. Now, that is the first layer of information, like how many number of M&Ms are traveling here. Second layer of information would be what type of M&Ms, what types of M&Ms are traveling here. So that's where Fourier transform comes in. Fourier transform tells us what are the constituent frequencies in a particular signal, or in our M&M packets, out of the total available M&Ms, what are the different types of M&Ms that are present in the signal. And this makes us easier to identify what are the important signal components in this particular signal, and based on that, try to find out what signal component does what. Okay. Now the third layer of information comes when we first know how does the signal look like, and then we find out the Fourier transform. So we know the time component, we know the frequency component, but we don't know the time frequency component. So now we do a time frequency analysis and trying to find out at what different times, what different frequencies are coming, and because of corrosion, that is our main problem, what is happening to all these frequencies. So this is our study that we have done, and I will quickly explain you what is happening here. So we are monitoring corrosion and different stages of corrosion by having a look at the signal strength and what the signal strength and how the signal strength changes with regards to different stages of corrosion. So the colored lines that are plotted here, they are basically the solutions from, they are the closed form solutions of wave equation. So basically what these lines say is, for a steel bar system at a particular frequency, what are the times of arrivals for different signal modes. We call these things as signal modes. So signal modes are basically like different types of eminence. So how fast or how slow different types of eminence are traveling. That's what we are trying to find out in our study. And here we have seen that so stage A being less corrosion and no corrosion, which is pristine, and stage F being highly corroded stage. We see that the signal frequency changes from a higher frequency, which is around 200 kilohertz, to a lower frequency, which is around, I think this is around 50 or 70 kilohertz. There is a reason why this is happening. So the reason is, I can quickly draw something for you. So basically, let's say there is a wave of a certain frequency, which is like this. Okay, I'll try to do again. So there is a wave of a certain frequency, which is like this, and there is a wave of a certain frequency, which is like this. So what happens is, as the corrosion pit size increases, first the wave of lower frequency, the wave of higher frequency and lower wavelength, they get affected, and then the waves of lower frequency and a higher wavelength, they get affected. So that's what is happening. If you look here, that's what is happening. The lower frequency waves are traveling, but the higher frequency components are gone. So we have done this study again with another different type of excitation. This is a 500 kilohertz excitation, and we have seen that this blob moves towards the left. So the higher frequency components are converted to the lower frequency component. And we have used a classifier, we have used a K-means classifier to classify how these frequency components, they change. So the higher frequency component, first it starts to fall down, then it stabilizes, and then it's gone. The lower frequency component, first it is not there, then it is picking up, then it is going up here, and after this particular point, it's trying to drop down. Because at this point, the corrosion pits are so big that all the signal is kind of dissipating. So we have found out different stages of corrosion: surface corrosion, transition corrosion, and pitting corrosion using ultrasonic waves. Now we have just talked about how these waves behave when they are excited by a piezo-based sensor or piezo-based device. Now we will see what happens when we use a high power laser system. So in the piezo system, we see the signal is focused in a very narrow banded region. But in a laser system, though it has higher energy, the signal is split, the signal is scattered. The signal strength comes at different frequencies, right? So that is a challenge to monitor different frequencies at different levels of corrosion. So the same experiment we have done with laser, and the laser with laser also we have seen similar results, that the higher frequency component, they dissipate and they go towards the lower frequencies. So this is a promising result. So thus we have established that with laser and piezo, by monitoring how much these frequencies have shifted, we can find out what is the level of corrosion. Now, the method that we have talked just now gives us an overall indication of whether there is corrosion or not. Now the second task comes is, once we get this information, can we zoom in and image that particular zone and find out what happens to corrosion or what is happening in that particular cross section. So this method is called ultrasonic imaging. So this is the second method by which we monitor our structures. So what we do is, we have a piezo transmitter, we have a piezo receiver, and what we do is we send a wave and we receive the wave, and we do it over and over again at multiple locations. And by combining all these waves together, we are trying to find out how the cross section of the wave, how the cross section of the concrete can be picked up. Here you can see there are two major interfaces in the structure. One is the steel bar embedded in concrete. Another one is the back wall or the bottom of the bar. So these two interfaces are clearly picked out here. And then there is a gap here because the bar is kind of shadowing the bottom reflection. So all this information are clearly being picked out. But because the way the transducers are positioned, we have this ghosting region. So this region is called as near field effect. So now, though we have got what we need to find out, But there are lots of other noises in the system. Now we have to get rid of the noise. So now we are trying to get rid of the noise. So we have developed a three-stage filtering algorithm by which we can filter this noise out. So in the first level, what we do is we are trying to focus the searching area of each transmitter and receiver location. And by focusing, we can see that we are already able to get rid of some noise. So this is the first layer of filtering. The second layer of filtering, what we have done is we are trying to improve the contrast by killing away the frequency by killing away the components which are of lower magnitudes. We have strategically adjusted these parameters, and we have found out how lower intensity reflections can be killed. Then in the third layer of filtering, what we are doing is we are doing averaging, and and based on this averaging, we are trying to precisely locate where the reflector is. So we are able to see the signature of the bar as well as the back wall. So thus, by using this three-layer filter, we are able to clearly find out where what particular embedment is there in concrete. This is a good layer of information. Now, with all this knowledge that we have got so far, we are trying to do a bigger problem. In the bigger problem, we are trying to monitor the steel bar corroding while it is embedded inside concrete. So as of now, we have done monitoring when the bar is outside. Now we have embedded the bar in concrete, and we are trying to find out whether all these corrosion activities can be picked up. We have done this experiment in few different ways. First, monitoring through piezo-based excitation. In this mode, it is called as a guided wave ultrasonics, because the wave is guided in the concrete by the steel bar. So the wave doesn't go everywhere in the concrete, but it is going only through the steel bar, and the steel bar acts as a guide. And the second method is acoustic emission, where we are not sending in any energy in the system, but we are just waiting for the cracks to happen. Because if we see how corrosion happens, so corrosion is nothing but an oxide layer, an oxide of steel, an oxide of iron. So the corrosion product forms between the steel bar and the concrete. And this oxide layer, it creates an interface between concrete and steel. And this interface grows, and when the corrosion product grows to a lot, then what happens is there are cracks that develop in concrete. And these cracks, they cause acoustic activity, and that are picked by the acoustic sensors. So this is how badly the sample was corroded. So we caused few decades worth of corrosion in few months in our lab by accelerating the process of corrosion. And we have seen that the bar is very badly corroded, and there is a big crack in the concrete because of the corrosion. And we are trying to see how the signal has changed because of the corrosion activity. So as discussed earlier, we have higher frequency and lower frequency block when we are using the guided wave mode. And as corrosion progresses, the higher frequency modes are gone. Very similar to what we have seen for just the bare bar. Also, we are trying to now superimpose this information with the acoustic emission information. So the yellow line here is acoustic emission information. So what we are seeing is, initially when there is corrosion, there is not much of acoustic activity. Then the acoustic activity picks up because there are lots of cracks that are developing between the concrete and steel interface. So these cracks are going up, and now from this point, the rate of increase of the crack has become slow, because the micro cracks have become macro cracks. So the big cracks have already formed, and the for the big cracks to become into huge crack, it takes a while. So the slope is slowing down. So the rate at which the cracks are forming is slowing down here. Thus, we have classified corrosion into initial stage, intermediate stage, and advanced stage. And we have done imaging as well. So initially in the image, what we can see is there is a clear signature of the rebar, and then the signature of the rebar disappears. and finally the rebar is gone. The reason is when there is corrosion, there are tiny cracks that are forming around the steel bar, and these tiny cracks, they kind of eat away the signal energy. And after a while, the tiny cracks become big cracks, and the big cracks eat away lots of energy. So when the big cracks eat away lots of energy, whatever energy we have sent, this energy doesn't come through. So that's why the signature of the bar is lost. So we have classified corrosion in 3 different ways. So this was my PhD work. Now I will present to you another application of bridge monitoring using waves that I did as my first postdoc work. So this work was kindly sponsored by Main Roads Western Australia. So Main Roads Western Australia would be equivalent to PWD department in India. So in Western Australia, we have around 1,200 small and big timber bridges, and some of these bridges, they support major highways. And the problem in these timber bridges is something called as piping. So what happens is, it's basically a timber bridge is nothing but a trunk of a tree. You can see they take a trunk of a tree, chop it down, and put it as a bridge. So while the rest of the world was building bridges in concrete and steel, Australia, they were building bridges with timber. It sounds counterintuitive, but if you look on a retrospection, the timber is a very sturdy construction material, and timber is available readily in Australia. And the idea was they will have timber bridges for about 40 years, and then they would get rid of the timber bridges and make like concrete bridges. But after 40 years, they realized that, well, these timber bridges are in very good shape. So they extended the timber bridge life to another 30 to 40 years. Now we are at the end of the second 40 year, and many of the bridges are not doing so well. So we have to find out what is happening to the bridges. So these are the two typical type of problems that are encountered by engineers who monitor bridges. So these are called this is called as pipe, because if you see here, this is a cross section of a trunk, and it actually looks like a straw, because the center part is a soft part of a tree, and the tree uses this soft part to suck in the nutrients from the soil. So what happens is, when the tree is chopped and it's used in a timber bridge, there is a moisture ingress. So moisture comes and ingresses into the soft part, and it deteriorates the softer part. And also there is attack from termites. So the termites, they love chewing on the timber, and they love the softer part. So once there is once the softer part is once the deterioration kicks in and the softer part is formed, the termites, they come in, they start chewing off timber, and they go from this stage to this stage. And from a civil and mechanical engineering point of view, basically what the moisture and termites are doing, they are reducing the second moment of inertia, I value of the particular timber section. As a result, the load carrying capacity of timber bridges reduces. So our task was to make a sensor that can find all this, because there is no way we can see all this happening, because this is all a continuous beam, continuous timber stringer. We call it a stringer, and there is no way to see what's happening in it. That was our task. So we started with building some numerical simulation models, and I'll just play the simulation video. There you go. The simulation video is on. So we have made the guided. We have put a guided wave sensor here. So basically, we are exciting the timber, which is here, through a waveguide, like the one that we have used for monitoring timber. And we are able to see how the signal characteristics has changed because of the presence of this pipe. Why is this happening? Because of attenuation or leakage. So when the guided wave is excited, a part of the wave stays in the bar, and a part of the wave dissipates into the timber. And when there is less timber around the bar, the leakage reduces, right? So that's why there is more energy in the bar. So if you see here, when there is deterioration, there is more energy in the bar. And when there is solid, there is less energy in the bar, because a lot of the energy gets let's say dissipated into the timber. So this is the basic operating principle of the timber guided wave sensor. This is how the sensor looks like. So these are samples that we got it from actual bridges, and we are testing in the lab. And there are some experimental results where we clearly seen there is more energy in the pipe case rather than the pristine case. And with this in place, we try to build a sensor that can be deployed on timber bridges in Western Australia. So we said that, okay, rather than modeling the whole timber, we will model only half of the timber, and our sensor in timber would look like this. Then we have done some more simulation studies into modeling this new sensor. And then we went from 2D, and these are all 3D results, and we have identified the zone which we should monitor and find out what is the amount of energy that is there in this particular zone, and based on that develop a model which will show how much is the deterioration. So these are some results, numerical results and experimental results, how they're falling close to each other. There are some laboratory results, and these are some implementation, I would say, in near field condition. So these samples, we did not introduce the sensor. So this is our sensor here. This is our sensor here. In this sensor, we have not got the sensor in an actual bridge, but this particular timber stringer was part of. I will just show you in a moment. So this particular sample was a part of. Go back again. Part of this bridge. So this bridge, they had removed some samples, and they had given some samples to us, and they asked us to find out what is happening in this bridge. So we done all this, and we are now monitoring this particular sensor, this particular timber stringer, and you can see that there is clearly a big pipe developed in this particular stringer, and based on our guided wave data and some confidence interval modeling, we are able to say how much is the solid. So at this location, the solid is between, we have a 95% confidence that the solid is between 130 mil and 145 mil. And in this particular region, we have a 95% confidence that the that the solid is between 80, if I remember, it's around 85, 86 something, and somewhere around 100 mil, which were very close to the measurements that were taken by the main roads inspectors. These are our inspection crew from main roads. So he's Wayne. So he was my boss from industry. He is the head of bridge maintenance and monitoring of Western Australia. These are our engineers from main roads. Yeah. And when it comes to technology that is there in the field, I will introduce you to some technology that is already being used by practicing engineers. So this can be an add-on to the knowledge base of practicing engineers who may be listening to this presentation later. So we have this thing called as an impact echo testing, where there is a portable tester which is used on concrete, and based on an impact resistance, the inspector can get an idea about how good the quality of concrete is. Again, this is an approximate method, not an accurate method. So this machine is a very developed machine. It uses a lot of these sensors, and using this sensing, using this machine, inspectors are able to go to a particular location and make measurements and find out what is happening inside concrete. I had the good fortune of visiting the lab which made this sensor. So this lab is in Berlin, and I was a visiting guest scientist last year in that lab, and they had kindly let me work with this machine and do some tests. And now we are working to find out how the imaging work that I had just shown you can be implemented on improving the results from this particular machine. It's called Mira. So it's one of the top of the line things that are available in market for practicing engineers now. Other than that, there are embedded sensors as well, which are being used. But again, the problem with these embedded sensors are there are some incidences of vandalism where people do mischievous things and they cut off the sensors. So if they do such things, then the information from the sensor is lost. Again, there is another type of sensor which is still in development phase. So this sensor, it uses an impactor. So it impacts the concrete surface and it measures, and there are microphones, and the microphones measure this response. and based on that, they are able to give an overall idea of what is happening to the road surface. Again, this lab is in TU Munchen. I've been to this lab last year as well. So yeah, interesting things that are happening. So interesting devices. Now comes to what I'm doing now. So now we are trying to build a monitoring device where we will excite concrete with a laser source, the laser source that I've just shown you, and we will measure using piezo and microphones, and we will try to give like an overall condition of the bridge, and we will find out what is happening in the bridge so that the inspectors get an alert and they can do further investigations. And this project is sponsored by Smart Grid CRC, which is a collaboration between federal government, universities, and industries in Australia. So this is my present role. This is our research group. So not only we do serious stuff, we do fun stuff as well, like outing, having a beer together, birthday parties, and just show off as well sometimes, which is nice. And these are my publications. So these are my journal article publication list. I have one book chapter, and I have a few conference articles as well. Before I finish, I would like to pay my respects to my grandfather who passed away peacefully yesterday. So rest in peace, Dadu. And thank you so much for all your attention. And I will now be happy to take any questions that you have. So thank you so much for your attention, and please let me know any questions that you have. Over to you, Manasvi. Thank you.
Thank you so much, Subhra, for this very comprehensive overview of how to monitor bridges. And I come from a botany background, so this is all very new to me and it's very interesting. I bet all the participants found that too. If you guys have any questions that you would like to ask, or just thoughts or any realizations that you had, anything you'd like to share, you can feel free to do that right now.
Hi, sir. Can I go ahead?
Yes,
Yeah,
please.
please go ahead. Please go ahead,
Yeah.
Hiran. You can address me by my name, Shubhra.
Yeah. So thank you for this wonderful talk. I just liked it. And my question is like recently one I have some seniors like who is working with like bridge monitoring, but with drones they are monitoring. So there's some kind of hyperspectrals are there. So using that they are monitoring. So if we are using that kind of like monitoring bridges through drones, so what is the difference type of information which we will get there, which we are not getting here, or like how will be that like useful compared to this?
Thank you, Hiran, for this wonderful question. So when it comes to drone inspection, so maybe what I'll do is I will go back to one slide which shows you this one. Okay. So with drone inspection, it is mostly visual inspection. So unless the damages they show up on the surface, we are unable to pick the information of the damage. But here, in case of corrosion, as we have seen, that unless the corrosion progresses to a very advanced stage, there are no signs of damage. The reason is, if you look at this analogy, so if you're able to see my pen, so if this is a steel bar, and if let's say this is concrete around it, so how corrosion happens? So initially there is a soft layer of rust that forms around the steel bar, and this soft layer it pushes the concrete, right? So and unless this push is strong enough to cause cracks, there won't be any surface cracks showing. So if you use drones, you will be able to pick up defects at a very advanced stage when the cracks have shown up and all that. So drone inspection is more like visual inspection, which can tell you an overall idea of the structure, but again, it cannot give you inside details. Like what is happening inside the structure, we will not be able to see. So to know what is happening inside the structure, you would need to send some kind of a wave into the structure, which would carry the information of what is happening in the structure, and then you would be able to predict how good the condition of the structure is. The present project that I'm working on, the Smart Grid project, where we are building an inspection vehicle, there we have different components of the project. So the idea of the project is to have a digital twin of any particular bridge. So where people would know all information about any parts of the bridge. So there, one part of the project is drone inspection. So the idea is to see at what stages of deterioration the visual inspection kind of shows up detail, whereas in methods like this, where we can get early detection. So the idea is to say, well, look, maybe the drone inspection is able to give us information at maybe stage C, stage D, or something like that. So yeah, so drone inspection can give one layer of information, but again, unless there are some visual signs, we will not be able to pick up information about damages that are happening inside concrete. So that's what I can say. Does that answer your question, Kiran?
Yeah, sure. Thank you.
Thank you.
Thank you, Hayden. Does anybody have any thoughts or questions that they'd like to share?
Wait.
If you'd just like to introduce yourself, maybe to Shubhra, you can feel free to do that too.
If you have any general questions as well, I will be happy to answer them as well, like life during PhD, life after PhD, how to find opportunities after PhD and all. So if you have anything to ask me, you can ask me, else I can tell you a few things. So after my PhD, like I finished my PhD in March 2020, and that was the time when COVID struck. So I was finding it difficult to get a job after my PhD, because there was tough situations, as well as yeah, people were trying to shut down because of COVID and all. That was a very challenging time for me, but luckily after some time we got this project with Main Roads, where they funded us to build a sensor for their timber bridges. So that was a very good learning experience for me, because yeah, we through this project we develop a sensor which has real world application that would potentially go and sit in the timber bridges and tell us how good these timber bridges are. Yeah.
Subhra, would you like to elaborate on your journey from IIT Gandhinagar to Curtin, if you're interested?
Yeah, thank you. So I finished my master's, and after I finished my master's, I had got an opportunity to do a PhD in Curtin University, which was a great opportunity for me. But before I could join, I needed some money to pay for my insurance and flight fare. So I worked as an assistant professor at a private college, where I was teaching undergrad first year students. It was a fun experience. I taught them for like less than a year, and then I moved to Curtin to start my PhD, and the experience of studying in an IIT and an overseas universities are very different. One thing is in IITs, you don't have to worry about cooking and keeping your, say, room clean or whatnot. You can easily hire resources. So here you have to clean your room, you have to cook for yourself, you have to clean your own lab, because if you make mess, then you have to do it. You have to clean yourself. You can't hire just people to do stuff for you. So that was a very interesting learning experience. So things are not easily available here. Let's say human resources is a big thing here. Also, another thing that I learned a lot during my PhD was health and safety. So it is very important to keep yourself safe while you're working in the lab, and also it's very important to keep others safe. So conducting regular checkups of your lab to find out what is happening in your lab and what's happening where. So that is very important. So that is something which I actually learned a lot. Maybe coming from India, we don't pay a lot of attention to health and safety. Maybe we think about it, but we hardly do things things about it, but here health and safety is very important. That's what I can say.
Yeah. Thank you, Subhra. And
Okay.
just give
Thank you. Maybe just go back to the last slide and say thank you to everyone. And yep, just 1 second. I just go here, cancel Discord. So thank you slide. Yep. Yep. Any other questions, queries?
Okay. Thank you, Subhra. Thank you, everybody, for being here.